seismology and things. Like he's interested in that, and he has some interest in meteorology. He's much more well-rounded. I just like math, and on occasion physics, and Legos. I'm cultured when it comes to Legos. I don't like just one kind. I like many kinds, but not the Frengelos. You know, those girl Legos. No, it's not for me.
Wasn't your major physics?
Yeah, my major. I had double major in math and physics, but before that, I have a 2-year degree in electronics engineering technology. If I had pursued that degree, I might be making more money right now. But we did op amps and digital logic design, all that stuff. It was fun. I was taking class in the morning. I was taking classes from Appalachian State University, which is in Boone, and then in the evening I had like night classes in like wiring at the time. So they're about 50 miles separated. So like my day would consist of driving. My parents lived right in the middle. It's like in the morning I'd get in the car, I'd drive to Appalachian, I'd find some parking here is not bad. Like Appalachian is bad. It's really, really bad. Like the parking lot's way on top of a hill. It's just, it's awful. So I'd find my parking spot, go to my Calculus 2. I think Calculus 2 and like Physics 232 here at App. And then I get back in my car, drive down 50 miles to the community college. Malin Community College. And why Malin? Well, Mitchell, Avery, Yancey. It's a tri-county community college. That's how sparse the population is there in North Carolina. And then I played pool on the quarter tables for like 4 hours until class started. It was amazing. It's so much fun. That semester, I was taking 30 hours. You know, you can take 30 hours if you do some at one college and another at another, and they don't know about the existence of the other.
In your time to play pool?
In between, yeah. But it was community college. I mean, it wasn't. That was fun.
30 hours and you had time to play pool for 4. How are you not studying all the time?
It was not bad. I mean, I don't know. I go home and do calculus problems after that. The thing that makes it easier for me is I enjoy it. So. You may or may not enjoy what you're doing, right? Oh, man. My apologies to the internet. I mean, I have taken courses I don't like, and I can tell you how much harder it is. Like, I had a course in graduate laboratory, which is kind of what it sounds like. It's like physics lab, but it's a 3-hour graduate course. It's the worst thing I've ever done. It's just awful. Despised it. I mean, I passed. I got my master's in physics, partly because of that, but oh, okay, so I'm sorry, I'm getting off track significantly. Let's see here. So let's try to recreate this using the thing I just covered up with the whiteboard. What was my system of equations was what? It was x1 prime equals to x2, and x2 prime equals to, was it minus 1 over m times the net force? But of course, aka dx dt equals to v, and dv dt equals to minus 1 over the mass times the force. All right, but let's see here. So our net force was, so we have to think v is y, so they have 1 minus 2x, yeah? And what was x? X prime is always y for these. Unexpected token. I'll give you an unexpected token. Let's see here. Sorry. ASCII for the win. Let's see here. Yay! As you can see, like I said, my picture is qualitative. You notice the shape of my ovals is a little bit off, right? By comparison. Okay, so here, this is fun while we got this out. What if we have solved these equations, spring force problems, right? Spring mass problems. What was it? MA equals minus kx minus bv, right? So this was the spring force problem. Now, so this would give us, let's set m equal to 1. So that would give us dv dt equals to, minus kx minus bv. So this would be my net force for the spring mass problem with friction. Let's actually look at some of those. What do you think the energy level curves are going to look like for that? Let's see here. Adjusting here, this would be something. Let's put k equal to 1 and b equals to 1 just to keep it simple. So I should have minus x minus y. Right? So that makes a lot of sense physically, right? This is a stable spiral. These, so if I could graph on, if you can get rid of, all right, just stare at this really hard, burn it into your retina for a second, okay? Got it? Good. If I get rid of the velocity term, that's making there to be no friction, right? Now we have, these are energy level curves, right? So these curves of constant energy, 1/2 kx squared plus 1/2 mv squared equals to a constant. When you add the velocity term, what you're doing is you're losing energy. I derived for you guys, I think, maybe I didn't. If you work it out though, you can show that for this problem, it is the case that the derivative of the energy with respect to time is minus bv squared. It's a good exercise to work that out. So that means that for B positive, the energy is always decreasing if there's a friction force. And it decreases proportional to the square of the velocity. The faster it's going, the faster the energy decreases. And so what you're doing when you add in that other term is you're sort of just, if you can imagine the frictionless system, you're just going to lower and lower and lower energies levels, and that's what those spirals are. You're toggling sort of to lower and lower and lower energies if we add back in that friction term. So we start out with a high energy and we go to always go back to energy 0, don't we? Wherever we start, we always end up energy 0. Is there anything else you guys like to look at? I mean, you could do other stuff, like what happens if you got more friction? Star, are you happy? Ooh, it's even more. It loses energy really, really fast, doesn't it? Ooh, that's funny. What's that?
What's the star?
Oh, multiplication. Huh. That's weird. It seems like there's some kind of... What's that? What's this line that's appearing? I was not expecting that. I'm not sure what that is, guys. Why is that there? I don't know. If you guys can explain it to me, I'd be interested. Let's see here. I mean, I think if I put a 4 here, we'll get back to what we... Huh. It's funny. Slope of -4. Huh. The other one had a slope of -1/4, yeah. Huh. Huh. Anyway. Let's see here. So anyway, that's energy analysis in a nutshell. You can easily plot the velocity versus position plane using this, discussion we've had here, and it's interesting, I think. Let's do one more autonomous system, then I'll stop talking about this stuff. So let's see here. Suppose we've got dx dt equal to x squared times y minus 2, and we've got dy dt equal to, I don't know, y squared minus y. What are the, oh. Well, yeah, let's just try to think about it. What are the critical points going to be here? Critical points need both of these being 0, right? So to get dx dt 0, I either need x equals to 0 or y equals to 2, right? How about this one? To get dy dt equal to 0, what do I need? Yeah, y equal to 1 or 0, right? So you put this together, to get both of these 0, we need either what? We could either do the origin, we could do 0, 1, and we could also do what? Oh, I guess that's it, isn't it? Like I could do 0, 2, just makes the first one 0. It doesn't help me with the second one, does it? So it looks like to me these are the two critical points for this system. Are those, what's the nature? What kind of critical points are they? What's the, are they stable? Are they unstable? What do they look like? Well, we can use p-plane to look at that. So you guys tell me, what's x prime equal to? I've already forgotten. Y minus 2? Yeah, what was the other one? Thank you very much.
So why isn't the 2? Why isn't the 2 being used?
So y equals 2. X equals 0 makes the top equation 0, but doesn't help us with the other one, right? Oops. Yeah. Let me make this. Yeah. Now there are, I don't know, I can't, for some reason I'm having trouble coming up with very interesting ones. Your book has a really nice like 4-page example where he has like 4 critical points and he discusses like these boundary curves between the regions of different critical points. It's very interesting. There's a deeper theory here to call known as the theory of, well, like there's Lyapunov's theorems. And I don't cover those in here, but if you wanted to study deeper, there's more to learn here, a lot more. I mean, people spend their careers studying these kinds of things. Dynamics and chaos is an ongoing and interesting topic. I had a student who went to Penn State, I think for an REU, and a fair amount of what they thought about was these sorts of questions like stability of, and sort of the question is you start out at some point and you do some sort of iteration, where do you go from there? That's where you get these like Mandelbrot sets and other things. It's a slightly different thing than this, but as you can see, it's kind of yucky, but the origin and what's the other one? 0, 1. So these are the two critical points. And let's see here. We've got these solutions flowing out, right? It looks like those solutions are flowing out. These solutions are flowing out. Oh, weird. Check that out. So like, to me, it looks like the solutions are flowing in from here, right? Is that right, though? I don't know. I might have to zoom in more before I made up my mind. This one definitely has some flowing in, but I guess they're flowing out here, aren't they? I can't tell. Man. I got to get closer. All right, so there's, if we look at it without the solutions, maybe it helps actually. So here's, where are we? 1, 0. They're going out like this. I'm not sure what's happening in these two directions. It's no help. Well, I guess, I mean, you can extrapolate. It must be coming in this way, right? And going out that way. So it's subtle, but I think this is unstable. Right? I mean, it's a saddle because it's got some going in and it's got some going out. Maybe it's just got one going in, actually, and everything else goes out. if you'd asked me to come up with an example where that happens, I couldn't have made it. I couldn't have done it, right? So I'm kind of, I should keep this one. This one's actually really, this makes a nasty homework question, doesn't it? Everything's going, well, like, so it looks to me like these are all going in, right? But that one's going out, isn't it? So maybe there's lots of solutions going out from that side, so to speak. I don't know. I mean, maybe it's just that one. Anyway, you see that these are kind of tough questions, like to really understand all possible paths going into these things without actually solving them. But you can gain some kind of qualitative information by just looking at this. All right, enough about that. Any questions? More to the point, if I ask you guys a question kind of like this or the one I did here, you know, do you think you have a shot at recreating something like this? Usually if I go slow and take like a whole hour to do it with you guys typically get this pretty well. There's always some subset of students who's ignored me when I talked about bounded motion, you know, or maybe I just talk about it and I haven't talked about it, I don't know, but I usually ask a question about bounded motion if I'm going to cover this topic because I think that's a lot of what's interesting about it. All right, so what's next? So we have covered non-homogeneous systems, we've covered the matrix exponential, we've just covered energy analysis. That brings us to the Laplace transform technique. And then past that, series solutions and the Frobenius method. And then, of course, test 2. So I have a quiz 2 and a quiz 3. When is quiz 3 due? I think these are both due before test 2. So 7-3. Oh, I still need to settle that issue. I think what we're going to have to do is we're going to have to say we're not meeting July 4th, and we'll push test 2 to July 5th, and the final we'll do on the 7th. Hopefully they won't lock us out of school. Yeah. Basically, we'll just take this part of the course and do this. And then correspondingly, the PDE project will be due a day later than what I currently have here. So I think that will give all of you a much better chance of really doing your best on the final. That extra day will help a lot. I really wish we would not schedule summer school during July 4th. Last time I taught summer school, this was also an issue. A few years ago, I taught physics 201 and 202 in the summer, which was an adventure. Weirdly, though, those students study better than a lot of you guys in like physics. Like you engineers in physics, like you guys like, this is just a gen ed class for me. It doesn't matter. This is an engineering. I don't care about this. It's not exactly high priority. And then, well, it's physics, so it's hard. It goes badly. But in 201, 202, I have a lot of med students. They care about their grades a lot. And so they really study. They are not as strong as you guys in terms of analytical skills. Like you're, on the average, I'm of course speaking statistically, but you know, your pre-calculus, trigonometry, these kinds of skills are much more, you're a higher skill set on the average than those folks. But their study habits, you guys could learn from. Not you guys specifically. Of course, I'm talking about other people right now. But
what is the PDE project?
It's not posted yet. The PDE project will be like, hey, here's 3 partial differential equations. Solve them. Most likely, yeah. It's nothing like, I'm not going to be like, not going to have to go to Home Depot and get supplies or anything like that. I mean, it's going to be, you know. Yeah, I don't think it will, I don't foresee it involving programming either. Although some computer algebra assistance might be wise. Because it probably will involve finding a Fourier decomposition of a function, which means that you need to integrate things multiplied by sines and cosines of arbitrary multiples of x. So I don't know about you, but when I integrate e to the x times sine of nx under time pressure, I might want to phone a friend just to be sure. I didn't miss a sign or something. What is going on here? Is it yours? I think it's... Oh, okay. It's fine. No problem, no problem. I was annoyed because I thought somebody was texting me, not because your phone went off. Let's see here. So, what I was thinking for today, and the time that remains, is I would try to give you a very fast introduction to... Oh, but I shouldn't do that because we still have another quiz. I was thinking I only had one quiz, so I should talk about Laplace transforms and series today. But I think we can just talk about Laplace transforms, and that's a wiser use of our time. So, actually, it's up to you guys. What would you prefer? Introduction to Laplace transforms and how to solve Laplace transform problems, or series? Introduction to series. Votes for Laplace. All right, fine. Very good. Now, ideally, I would like to give you a sheet of Laplace transforms to look at while we're doing this. Unfortunately, I forgot to do that. So, come Monday, though, I should probably have a sheet for you. Let me see in the book. We do have a book. We should use it for something. I mean, basically what I did was I took some of the theorems in Chapter 7, and I kind of gathered them together. Table 7.1 on page 358 is pretty good. And I really need to create a new, I'm kind of tired of my Laplace transform sheet. I need to create a new, better one.
What was that table say?
Table 7.1 on page 358 is not bad. So let's talk about the Laplace transform technique. I'll show you guys how to do it. Actually, for the sake of silly labeling,